So when is our second exam? Is that
great question. Going to say that. No, not this Saturday. Don't worry. I was planning to do it for next Saturday, the second test. I could also give it to you over Thanksgiving weekend, but I felt that would be bad. So yeah, next weekend you should expect to have the second test out, and it'll cover. I'll send out an announcement, but it should cover the interference and polarization topics, which will be winding up interference today. Okay. I also see that the old threat of the pop quiz has helped to bring the attendance back up. Sorry, I had to resort to such draconian tactics, but you didn't give me much choice. All right, let's talk about interferometers. We already covered the Michelson interferometer in the last class, and we said that there are dark fringes at the center due to the phase shift when there's one internal and one external reflection in the partially silver emitter, and we saw that that means that we get the dark fringes where usually we would have got bright fringes with m lambda naught, where m being the order of the fringe. Now we get a dark fringe, and so it looks very similar to Heidinger fringes. Yeah, so it looks very similar to Heidinger fringes, fringes of equal inclination. And so by putting a large lens there, we can see the entire pattern, which will be circular. And there are many applications. We went over one application like a problem in the last class, an example where we saw that you can use it to measure the index of refraction very accurately. I mean, I did it for something that was very simple, a plate of glass. But in actual experiments, you can put in like a gas or some other material that's really hard to measure, and this will allow you to measure that. Another sort of application that is often used, for example, in space, when people want to look at like infrared wavelengths and how do you measure infrared wavelengths, it's kind of hard when you use regular prisms or glasses and things like that, because a lot of times the infrared gets absorbed, okay? There aren't many good materials for infrared, and plus also the dispersion is very different in those wavelengths. So the Fourier transform spectrometer, as the name, it's a fancy name, but it really is just a Michelson interferometer, which has been set up to create patterns with infrared wavelengths. So these are often the spectrometers that are sent out into satellites and things like that. And another application that, again, might be familiar to some of you is LIGO. So the LIGO interferometer is basically a very large baseline Michelson optical interferometer. And we'll cover maybe a couple other applications as we go along. Okay, I wanted to introduce one other interferometer, which is very interesting, or at least is also widely used, which is called the Mach-Zehnder interferometer. And in this case, instead of like having just one beam splitter, we have two beam splitters, and we have two mirrors again, just like before. And again, by like moving one of the mirrors, we could like change the path length. But basically, the idea is that we're going to. So, for example, if everything was equal in this situation, if all the path lengths here were equal of the two arms of the interferometer, then what you'll actually get is that both the beams will undergo external reflections at the beam splitter, as you can see from following along in this expression or in this interferometer, that they'll both be undergoing external reflections at the two beam splitters, and therefore you get a bright fringe when you come to this detector. Okay, this detector over here. Okay, I'm not stepping through all the details. But in the other direction, going upward, one of the beams has to undergo an internal reflection of the beam splitter, so you get destructive interference over there. Okay, so for example, if there's bright here, there'll be a dark here, bright, dark, bright, dark. And so that's very nice as a contrast. So it helps you to like get rid of what we call common mode noise in the beam splitter paths. And that helps you to then like only figure out what are the phase changes between the two beam paths. So again, as an application, you could imagine I insert some reference cell over here, and then I put a cell containing a gas that I want to measure. And now because you have zeroed out all these like common mode path length changes, like if everything moves by the same amount, nothing will happen in this situation, because again, you can like zero out those kind of fluctuations by looking at the difference between the detector signals in one arm versus the other arm. Okay. So many applications again of the Mach-Zehnder interferometer. One of the most important ones, probably for like day-to-day life, is fiber optic modulators for telecom. So, for example, all of the telecom switches and so on all have fiber optic modulators that are essentially small Mach-Zehnder interferometers with like an electro-optic element inside them. And in other sort of applications, visualizing flow in like wind tunnels and plasmas and heat transfer, again, it's difficult to observe those changes because, the wind or whatever might be flowing and it's hard to see changes in the phase of the light, etc., except by using a Mach-Zehnder interferometer, we can measure that. And then certainly in experiments that are close to my research are things like quantum entanglement experiments. We do some quantum entangle experiments. We set up Mach-Zehnder interferometers for those as well. Also holographic interferometric, double R. All right. Other interferometers that you might encounter. One is this famous Sagnac interferometer. This is a ring type interferometer. It's used in laser gyroscopes, which are laser ring gyros are famous because they can be used sent up on aircraft and things like that to like measure the rotation of the plane. Like you can use that, like how a gyroscope works. You're probably all familiar from like undergrad, the first and second year physics. But this is now a more sensitive way to measure that using light rather than having a spinning object directly. Anyway, so laser ring gyros, but also laser cavities. So we also use them in laser cavities. So that's another useful situation. Here's another one. I just threw up one or two that have applications, like the pole interferometer is often used to measure like variations in thickness of a film. This is just illustrating with like a mica substrate, but you can use it on like thin films and so on to measure variations in the thickness of the film itself. Okay. All right, let's do another example. So a Michelson interferometer is used to resolve the D1 and D2 lines of sodium, which are at a wavelength of 589 nanometers approximately. And there's a spacing between the two D1 and D2 lines. Again, another application for Michelson is like stellar spectroscopy. For example, you have like atomic lines from some star or something that you want to resolve, you can use the Michelson interferometer. But coming back to this problem, so to measure this separation though, which is too small to be resolved directly with a typical spectrometer like the ones that you might have used in your first or second lab with a prism, etc. So to measure this separation, we follow the following procedure. We take a micrometer on one of the mirrors, M1 or M2, whichever that you've probably seen in your lab, and we move it till the bright fringe from one wavelength, the D1 line, overlaps with the dark fringe from the other line. Okay, we call this washing out the pattern. So you can understand one wavelength produces bright, dark, bright, dark. The other also produces bright, dark, but slightly shifted because they're a slightly different wavelength. Okay. So if you now move the micrometer till the dark fringe from one appears on the bright fringe of the other, you've basically washed out the interference pattern. It's like if I took like a comb with like, the spacing like this, and I took another comb which is slightly more spread out, and I start to move them against each other. Now you can't see through the combs as they are moving across each other, right? It's just the same idea. Like it's just a bunch of like lines or bright and dark patterns. And then as I slide these across each other, I'm going to get sometimes, now suddenly you can't see through, like, and everything gets washed out. Okay, so first what we do is we move the micrometer till this washing out of the pattern happens. And then we record the micrometer position. And then we move the micrometer till we get a bright, like everything looks crisp again. And then we move it till we observe the next washing out of the pattern. So basically what has happened is M or N, whatever you want to call it, N fringes have moved such that the N fringes of this one have overlapped with the N plus 1th fringe from the other pattern, because the other one has to shift by exactly one fringe over such that the dark fringe overlaps with the bright fringe of this one. So if this moves by N, the other has to move by N plus 1, basically, so that the dark and the bright fringe patterns overlap. And you observe in the experiment that this washing out happens when you move the micrometer by 306 microns. So now we want to ask what is the spacing of the two lines between D1 and D2. Okay. So any thoughts on how to start the experiment, the calculation, knowing this, I've tried to explain the whole idea of it. Hopefully that was somewhat clear, but if not, you can talk among yourself and think about like how you might answer this question. Did the explanation make sense of how this experiment is carried out and why it's having these repeated washing out and crisp and so on? It makes sense. Any questions, but please talk to your neighbors and tell me what you think I should do to calculate this.
It's like something unfortunate about this things.
Yeah, I mean, but before we get to the final answer, like what should we set equal to what? If I have like these end fringes moving past one another.
That's a no.
Not sure what I'm talking about.
Yeah.
Okay. All right, so maybe I didn't make it too clear. So what I'm saying here is that when I move the micrometer by some distance d, let's call that d, right? And I've just said that n fringes of the first wavelength have to move past, and then n plus 1 of the other fringe have to move past, right? So let's say the first wavelength is lambda 1, the second wavelength is lambda 2 for the D1 and D2 lines, okay? So how much does the path length change when I move the micrometer by a distance d? How much is the change in the path length? Yes? No? Twice d, exactly. So the path length difference on moving the micrometer is 2 times d, the distance that the micrometer moves, right? Everybody okay with that? And now, when this happens, I've just said n fringes move past for the first wave. So by how much does the path length change in terms of the lambda 1 for that particular wave? So I've said n fringes move past, how much does the path length have to change for that particular wave? How many repetitions have happened? Yes, Stephanie? Exactly. So that must be equal to n times lambda 1, right? And at the same time, I've said n plus 1 fringes moved by for lambda 2. Therefore, this must also be equal to n plus 1 times lambda 2.
Mm-hmm.
Everyone good with this? Right? So if I equate n lambda 1 equals n plus 1 lambda 2, obviously I immediately get lambda 1 minus lambda 2 is equal to lambda 2 divided by n. Okay? Everyone okay with this? And at the same time, I've said that we initially started with a bright fringe, or we had n bright fringes move by. So that means n lambda must be equal to 2d. Okay? Therefore, n or lambda 2 must be equal to 2d. So n equals 2d divided by lambda 2. Okay? Therefore, we have that lambda 1 minus lambda 2 equals lambda 2 divided by 2d over lambda 2, which is lambda 2 squared divided by 2. And this is approximately just, lambda squared, because as I said, the two of them are very close to each other. And therefore, we can set that whatever the wavelength, central wavelength of lambda as the state for both of them in this situation. Okay. Everybody fine with this calculation? How it's carried out? With this is really an approximation right here, where I've set n, it should have been n plus 1, but I just set that as n. That's what I'm trying to say. For this part of the calculation, the 1 doesn't matter. All right, so basically, okay, I guess I should have finished the statement, which is now just substitute the values. So you put lambda, which was given to you in the problem, and you put in the distance, and you calculate the difference between lambda 1 and 2. So I'll just leave that to you. Sorry. Okay, so that was my last example with interference of Michelson. Again, these are problems that you fully expect to see on your Michelson tests. So hopefully you understood it. Okay. All right. So now I want to move on. Okay, let me do this section, then we'll do the pop quiz. Okay. All right. So this is an important section. So because as you will see, the technique that we use here for this section is going to pop up all over the place in other situations as well. Okay, so now we're going to consider, remember the dielectric film and the multi-layer films that we talked about with like anti-reflection coatings, with like, we've talked about these films and reflections from films ad infinitum. But now we are going to add in, or to put in, that previously we were considering the first reflection, and then the reflection inside the film, and then we were just considering the interference between those two. That was our Heidinger fringes, or fringes of equal thickness, etc., etc. But now what we're going to do is we're going to assume that it's not just one reflection, but we can have additional reflections. So, this one undergoes one reflection in the film and comes out. This one undergoes 2 and 3 before coming out. So 3 reflections total. This one will undergo 5, 7, etc. reflections inside the film before it comes out, and all of these can interfere on your final detector. Okay, so to calculate now, we need to sum up, of course, the waves, the fields from all of these, and we need to take into account the fact that this that at each point of these of this film, the amplitude may not be exactly the same as this one. Okay, so for example, this one is E naught times R. Sorry, this R should, I guess it's reflection, but it's also E naught multiplied by R, the Fresnel reflection coefficient for the film going from N1 up to NF. So, and by the way, yes, so here's our situation. This is N1 is the refractive index over here. N2 on the other side, we set it equal to N1 for simplicity. You can do the more general case, but we won't deal with that here. And then this is NF, the film refractive index. Okay. And you see here now that this first beam has a transmission coefficient E naught T, gets reflected, so that's E naught T R prime. So we are calling the reflection from the film into the medium, into the incident medium N1 as R prime. Okay. And so we're denoting by R and T the reflection from the external. This is external reflection, and then the internal reflection is with the primes, and also similarly with the transmissions. Okay. So this is T, and then this transmission over here has a T prime. Okay. So that is just E naught T R prime T prime. Okay, and this is E naught times R. Okay. And then similarly, the next one is undergoing another bounce here. So this is becoming E naught times T times R prime squared, because of this is the second R prime. And then because it undergoes yet another reflection, that becomes R prime cubed. So R prime effectively tracks the number of bounces inside the film. Okay. All right. So another thing we want to take into account is the phase shift. We already know this result, which is that there is a phase shift between the internal and the external reflections of pi, which is that r prime equals minus r. That is the magnitude of r prime, which is the reflection internal in the film, is equal to the magnitude of r, except that there's a phase shift or a sign shift between r prime and r. And I'll show you another way to know that result even without knowing the Fresnel coefficients in just a minute. Okay, there's a very beautiful argument from Stokes about that. Oh, and by the way, we can also write down all the transmitted beams as well. Okay. So because it undergoes an odd number of bounces, so the first one has r prime equals minus r, the second one is r prime cube, so that also is minus r cube, etc. Okay. So, and let's assume, by the way, in all of this, I haven't taken into account the path length difference or the phase difference between each of these fields. As we know, if there is some optical path length inside this medium, then of course there is going to be an optical path length difference, which is given by 2 pi over lambda naught times this big lambda, which is the optical path length. Okay, so that's the phase difference between the two beams or between each of the beams. So the first one might be 2 pi over lambda naught times lambda. The next one will be, times 2 lambda, etc., etc. Okay. All right. So since we are assuming that's an integer number of wavelengths, that is, if capital lambda is equal to m times lambda f, where f is the m times lambda naught, because the optical path length already takes into account the refractive index. So if that is m times lambda naught, which is an integer, then we know that's equivalent to multiplying by e to the I 2 pi, meaning that it's like a 2 pi phase difference. And a 2 pi phase difference then is just equivalent to multiplying by 1. So the E naught, the field is just E naught R, because that's the first reflection, as we've already seen. And then it's every one of these guys has a minus sign because of the fact that there's a minus sign for the odd number of bounces. And then it's just T R T prime. It's just this expression with r prime replaced with minus r. Okay, so r prime replaced by minus r cube replaced by r prime cube replaced by minus r cube, etc., going on effectively to infinity, right? That's the idea. And I claim that this is equal to this result over here, which is fairly straightforward. It's just a geometric series. Do I need to review geometric series? If you need me to, I can. It's okay with geometric series? Just state that. Okay, very good. So if you're not sure, please don't hesitate to ask me, but I'll just quickly write down. So basically I can take out T R T prime from this series over here, and E naught, of course, as well. It's common for this big bracket over here. And so this is just 1 plus derivatives plus r squared plus 4 plus infinite series, and that is essentially 1 divided by 1 minus r squared. It will converge to that as long as the magnitude of r is lesser than. Okay, so that is the geometric series. So that is just that result over there. Okay, and I claim that E naught r is therefore 0, because it turns out that T prime is always equal to 1 minus r squared. That seems very strange. How can that be true for any? I'm claiming this is true for any film refractive index, any angle, doesn't matter. T prime must be equal to 1 minus r squared. Assuming the film doesn't have absorption inside it. Of course, that could destroy this criterion, this statement. Okay, I claim that this is always true. That is, if the optical path length difference is an integer number of wavelengths, I'll get perfect cancellation for this film. So we have derived now a way to show that this is true for like perfect, for multiple beams. Okay? As long as this, of course, we're assuming this Tt prime equals 1 minus r squared, but I'm claiming that's always true as well. Okay. This was proven by George Stokes, I can't remember when, and this is such a beautiful proof that I have to show it to you, even though it's not strictly necessary for you to know it, but it's just so, it uses those arguments that we physicists love, which is symmetry. Okay. All right. So let's look at this situation for a single beam. So we have an incoming wave in a medium of refractive index n1 going into a medium of refractive index n2. The angle is θ1 here, θ2 over here for the refracted beam. And of course, we have the reflected beam as well. And as we have already said, the coefficient of the Fresnel coefficient for this interface is R. The Fresnel coefficient for transmission is T. Okay, small t. What George Stokes realized was, suppose I time reverse the whole situation. So now instead of one beam coming in and two beams going out, imagine I have two beams coming in, one from this angle, one from this angle. Well, everything has to look the same, right? Because it's time reversal invariant, or principle of reciprocity that we read about, that we talked about when we did Fermat's principle. Everything has to look the same when I reverse the path of the beam. So what must happen is that these two beams must combine perfectly to give me this outgoing beam, which is having the same magnitude 1 at this point. So this is the situation in the time reversed world where I run time backwards, and this must be the same as that situation over there. This must be true. Okay. So a beam with amplitude R and a beam with amplitude T must combine to give me the amplitude 1 going backward. Okay. Well, if that is true, but we know that the Fresnel coefficient of going from N2 into that medium is not T anymore, it's T prime. So this beam will be transmitted with the coefficient T prime in front of it. So it's T times T prime going in this direction. And this beam, which is coming from here to here, is of course again reflected by an amount R, so it must give me R squared. So these two beams combining will give me R squared plus Tt prime, which must be equal to the incident amplitude 1. Okay. So that's just drawn there, Tt prime, and also I should mention, of course, there must be a reflection of this beam at this interface, which must be R prime, T times R prime. That's the green. That's what will happen to this beam when it hits this interface. Okay. Similarly, this beam will get that R squared reflection that I just talked about, and also, of course, it has a transmitted part which is R times T as well. But we know there's no beam over here, so these two must add up to 0 as well. So we get two Stokes relations for the price of 1. Okay, and that is these two relations over here. T R prime plus RT must be equal to 0. And R squared plus Tt prime is equal to 1, which is the relation that I just used in the previous slide to say that that reflection, that the sum of that series must be 0, or the sum of the two of that situation must be 0. So looking at this, there is one little subtlety. We also therefore derive that R prime equals minus R from the top relation. Okay. But there is a subtlety, so please bear it in mind, because when we time reverse the situation, this thing still comes in at the same angle θ2. And this thing goes out at the angle θ1. So what I'm really saying is R prime at the angle θ2 must be equal to minus R at the angle θ1. Okay, so the angles are important. I'm not saying R prime at θ1 is equal to minus R at θ1. Okay, so if you go back and look at the Fresnel coefficients for these situations, you would find that as long as you replace θ1 by θ2, then R prime θ2 will be equal to minus R θ1, but not if you kept it as θ1 at all times. So I'm not saying that there's no difference between the reflection from a beam going from N2 to N1 versus N1 to N2. There is a difference. But as long as you change the angles as well, you'll get the same answer. Okay, so this is the Stokes relations, and it's such a beautiful argument I had to tell you about it. Any questions on this? Okay. All right, so we are now going to talk about the phasor diagram. I like to talk about the phasor diagram here because it starts to introduce this thing which we're going to use a lot in the subsequent theory of diffraction as well. Okay. So remember, we have said the optical path length difference lambda is m times small lambda, lambda being the wavelength. And I'm claiming that this gives me destructive interference. And that's because if I go back to this picture over here, I have this first phasor, and then every subsequent phasor is minus the first phasor, has a minus sign in front of it. Okay? So from this, I must subtract every subsequent phasor. And if they are exactly integer multiple of wavelengths or a phase shift of 2 pi, if there was no minus sign, they would all line up in the same direction. The phasors would all line up in the same direction. But because of the minus sign, there is they all line up together, but opposite to the original. So the first one, which is probably the biggest one, because it's the first reflection, this is the first reflection, and then the second reflection, which is opposite in phase, is slightly smaller than the first one because of the factor t prime r squared, and therefore it is slightly smaller, and then the next one is slightly smaller, but they all are basically negative to the first reflection. And of course, the claim is that we have shown by this geometric series that the sum of these guys must be equal to exactly E naught, the original amplitude. So therefore, the total reflection E naught times R, where R is the reflection coefficient for the first reflection, and so the resultant must be 0 because it all adds up to converge. It's like that old tortoise situation where the tortoise only goes half every step forward, but in the end it will still reach the destination because the geometric series converges, right? Same idea. Okay. Whereas if the path length difference was m plus half lambda, then even though the first reflection should, or the second, this is the first reflection, this is the second one, even though the second reflection should be, pointing in the opposite direction, but because we have added this plus half lambda at the beginning for m, for the first one, therefore this one will still be in the same direction. Okay. That one will still be in the same direction as the first one, but then every subsequent one again will be opposite in sign to this first one. And therefore, this sum, even though it's not as big as the original one, because all of these guys subtract from this first one, it will still give me some overall resultant amplitude. Okay, and therefore, m plus half lambda will still give me some intensity coming backward from the film. Now we want to do the most general situation. Okay, so now I'm going to add up n phasors. Okay, n going to infinity, of course, but we can do it for finite number first. So the first phasor is E1R, second phasor is E2R, E3R up to ENR. So again, I draw the first phasor, okay, and then the second phasor, which is E0T R prime T prime. Sorry, the first phasor is just E0 times R. Okay, so that's already there. The second phasor is E0T R prime T prime. Sorry, just going backward a few slides. You'll see that. E0R plus E0T R prime T prime. But now it's shifted by an angle delta. That's because the phase difference is no longer 2 pi or pi, but it is some arbitrary angle. So I'm assuming we are looking at situations where the phase difference may not necessarily be pi or 2 pi. Okay? So that's what this situation is meant to indicate. So the second reflection basically is off by an angle delta because of the phase difference. The next one is an additional delta, right? Every time I go through the film, I pick up an additional delta phase, and you can already intuitively see this is going to sort of start spiraling into some value, and that is the resultant phasor value. We are adding up all the phasor amplitudes. So now we can do this. This is a geometrical picture. Now we can do the algebra of this picture. Okay. So the first phasor is just E naught times R, and of course there's the e to the I omega t, which will be common to all of them, or minus I omega t. It doesn't matter for this particular situation. Every subsequent one has an extra amplitude, which we've already derived, the T R prime T prime, T R prime cube T prime, and then finally T R prime 2n minus 3 T prime. It's just count up the number of phasors, and it's 2n minus 3 for that R prime factor. And the TT prime is common to all of them. And then for each additional one, you get e to the I omega t minus 2 delta, and then this one will be e to the I omega t minus n minus 1 delta. Okay, again, we can follow the same approach. We pull out any factors of E naught I omega t and the R, and then we get this relationship. Again, I'm just using the geometric series, except the geometric series that I'm taking into account. And by the way, I should have put R prime equals minus R as well. That would have made this a little simpler. Sorry, I didn't do that, but you can do that yourself. Just put R prime equals minus R. This expression. Okay. And of course, this is also only valid in n is very large, and also this R prime squared e to the minus I delta is lesser than 1. Okay. Okay, so that was for the most general case. And that's actually what we need to now calculate the expression for the intensity. Knowing the phasor, I can find the intensity by taking ER times ER star, its complex conjugate, and dividing by 2. Okay, so that's ER square star divided by 2. That's the reflected intensity from the film. And that, okay, now I'm just going to skip all the math details because it's just basically boring algebra of taking the complex conjugate, multiplying it all out, simplifying cosines. I'm not saying it's easy. It can lead to sometimes trouble if you're not careful, but hopefully you can carry it out. If you're having trouble, please come and talk to me. I'll help you through it. Okay. Okay, so that gives me the reflected intensity. And then I can simplify it further by writing 1 minus cosine delta is 2 times sine squared delta over 2. And that's another additional simplification. So that helps me write this out in this form so that we see there's this factor 2r divided by 1 minus r squared. This is called the coefficient of finesse. Oh, and the delta, in case you've forgotten, is just simply, again, always remember this. It's 2 pi over lambda naught times the optical path length difference in the film, which we already said the optical path length difference is 2 nf times d times cosine theta, the angle. So this is effectively dependent on the angle here. Okay. So everything that is at the same angle will have the same phase and therefore the same intensity, which means, again, we get circular fringes when we look at this system again. We can also do the transmitted intensity, same way, which remember we already had those factors written out. And again, we get something which looks like this. There is this factor 2r divided by 1 minus r squared. That is defined as the coefficient of finesse, 2r minus divided by 1 minus r squared, the whole square. You can see what this is doing. If r is very large, almost equal to 1, right? Then this guy is going to be very high, the coefficient of finesse. Okay, and we'll see what that means in a second. The delta I've already written down. I'm just repeating it here. I get that the reflected intensity is this f sine squared delta over 2 divided by 1 plus f sine squared delta over 2. And the transmitted intensity is just 1 divided by 1 plus f sine squared delta over 2. If I plotted that's called the Airy function. It's a famous function. And if I plotted this now as a function of delta, which remember is also dependent on lambda, the wavelength, and on the film thickness and the refractive index and the angle. Okay, so that's the factors in there. So usually, typically, we'll keep one of these fixed and vary something else to watch this. And you can see here what happens if the coefficient of finesse is very large. Okay, as this gets larger and larger, the peaks get very, very narrow. Okay, so what this is effectively it's a very effective filter in the delta space, or equivalently either in frequency or in the thickness, whichever one you want to vary. You can make this as a very sharp filter for those things. So usually frequency, okay, will be one of the things that we can vary, frequency of the wavelength, frequency or the wavelength of the light. And you can see for f equal for like f equal to 0.2, which is a small coefficient of finesse, you get something that looks almost like a cosine squared distribution, which is what you would get from, say, just a standard intensity of two beams that are interfering. Okay, but as we make f larger and larger, which is basically making r squared larger and larger, approaching 1, right? Then we are going to get sharper and sharper peaks in this in this function, which is the Airy function. Okay. I know I'm running out of time, but I want to quickly go over some applications. So this is called the Fabry-Perot interferometer, which is just basically exactly what we have looked at. We have a film, but here the film is defined by two mirrors, okay? And so if you take two parallel mirrors and fix them at a distance d apart, then everything that I've just said works in exactly the same way. So here's how the system is set up. You have a broad source or maybe a laser beam, whatever. And you send it through these two mirrors, which are spaced a distance d apart. And then you can, of course, as usual, have a focusing lens. And that just gives me circular fringes in that screen. And it's commonly used in high-resolution laser spectroscopy, in resonant cavities for lasers. There's two different words here. One is echelon and one is interferometer. Echelon is, because the spacing between these mirrors matters so much and the fact that they had to be exactly parallel to each other for this all to work correctly, often what happens is people attach two mirrors to like just rigid rods made of like Invar or a quartz block and just attach two like very nice mirrors to the quartz block, okay? Because quartz and Invar are both very low thermal expansion materials. And quartz, of course, is very transparent, so it's also very good for that reason, okay? For Invar, you have to do a little bit more machining and things like that, but anyway. Okay, so all this is saying is that this has a, and we can make it an interferometer if we can then slightly adjust the spacing, either with like a piezo or some other material that will move the interferometer slightly, and we can get these very sharp fringes, much sharper than what you would get from Mach-Zehnder interferometer, for example. Okay. The last thing I want to point out is that the Fabry-Perot echelon has just by simplification of that expression, there's this AD function and then there's this factor in front. The factor just comes from the fact that instead of just having transmission and reflection, you may have some absorption. So that's taken into account in this extra formula here. It's not super important to know that factor, but it's there. And then we have the AD function as usual. And that allows us to define something called the finesse. I know it's not a very good, physicists are terrible at names. I've said this before. We already defined a coefficient of finesse, but now we're going to define another thing which is called finesse, but it has a different meaning. Okay. Okay. And this is probably the one you care about the most. Okay. The finesse is kind of giving you a ruler. Okay. And it's telling you what is the minimum sort of resolution of this ruler. Because think about this delta, which is which I've already written down a few times. It's 2 pi over lambda naught times the optical path length difference. This is on the x-axis. Well, if say lambda naught varies, which is equivalent to the frequency vary, because lambda naught is just 1 over f or c divided by f. So that means when the frequency varies, so if I imagine sweeping out the frequency slowly, every time I hit one of these peaks, I would get a high transmission, and then it will go away to 0, and then I'll get again a high transmission. So if I have two such wavelengths, I'll see two peaks here, which are slightly separated in their frequency, right, in their peaks, where the peak is happening, if the frequencies are different. So again, this is just like the Mach-Zehnder interferometer example, but now I have a much sharper way to distinguish because the two peaks are resolvable as soon as they exceed the width of this initial peak. Okay, so if I had only one wavelength, this would be the width of the peak. Okay, with two wavelengths, I'll have a small, gap in between, and they'll become resolvable as soon as that gap is greater than the width of this peak. What is the width of this peak given by? It's given by the finesse, because it's the separation, the finesse of the echelon is the separation between the peaks, which is called the free spectral range, divided by the width of the peak. So it tells you how narrow these peaks are. If the finesse is very large, usually free spectral range is just fixed by the spacing of the mirrors. But the finesse is given by free spectral range divided by the gamma, the frequency width. Yeah. Question.
So how do we just describe the interference between these two? So how do we just characterize that?
Interference between what and what?
Yeah, there are two peaks, and then we treat the...
So if I have two wavelengths, let me try to draw it here. I'll have one wavelength giving me a peak, and then I'll have another wavelength giving me a peak.
Yeah.
And so the separation between these two is resolvable, and I'll I'll make the criterion more robust when we talk about this in more detail, but really you can already see if this separation is greater than gamma, right, where gamma is the width of the peak, I can see it. As it becomes less than gamma, it becomes harder and harder to see. And different people have different criteria. Raleigh came up with one criterion which said that if the two peaks, if the wavelength separation is exactly equal to the width of the peak, then it's separate, you can separate. Other Sparrow came up with another criterion. Okay, so I won't get into all the details. You can read about it in spectroscopy textbooks. I'll come back to the Raleigh criterion later because it's also helpful for resolution of optical systems. But this is the basic idea. It's very straightforward to understand. You have two peaks, and as soon as the separation becomes greater than a line width, the width of this peak here, they become resolvable. That's one criterion that one can make. Okay? Of course, nowadays with modern technology, with like computers and so on, you can get the data, you can fit it, and try to like make that resolution much better by just using fitting parameters. You can say, okay, how good does it have to be to know the separation? Well, okay, now various things like how good is your resolution, how good is your signal to noise, digitization, all these things come into play. So this is just like the old criteria, the way people used it because they were using their eyes, they were using photographic film to tell what is going on. So they came up with one criterion, but we don't have to use only that criterion. Okay. That's more an experimental thing. Okay, we are out of time, but let me try to show you let me stop the share. And let's see if I can show you the quiz. I'm sure that's why you came. Okay. Let's quickly go over the quiz. All right, the first one, maybe tricky one. Yes, you didn't.